The physics of a fusion plasma is gorgeous and slow. A first principles turbulence simulation can run for hours or days on a supercomputer to model a fraction of a second of plasma. That is fine for understanding, but a machine that must react in milliseconds cannot wait on a calculation that takes a week. This is the problem surrogates were built to solve. A surrogate is a fast stand-in that learns the behavior of a slow physics model. You run the demanding simulation many times offline, where compute time is plentiful, and you train a model to reproduce its answers. Once trained, it gives you in microseconds what the full simulation gives you in hours. Not perfect, but close enough to act on and fast enough to use in real time. Its education comes from simulation. High-fidelity codes generate the training data, thousands of carefully chosen cases spanning the operating space we actually care about. And the surrogate learns the map from inputs to outcomes across all of them. The physics is the teacher. The surrogate is the fast student. And because the teacher is a trusted simulation, we can generate exactly the examples we need, where we need them. Part of the trick is reduction. A full plasma simulation may carry millions of degrees of freedom, of value at every point of a fine mesh. But the behavior that actually matters often lives in a far smaller space. Model order reduction compresses those millions of variables down to hundreds, keeping what genuinely moves the physics and discarding what does not. Smaller is not just faster, it is often clearer. One classic way to find that small space is to watch the plasma and extract its dominant patterns, the handful of modes that carry most of the dynamics. Methods like proper orthogonal decomposition and dynamic mode decomposition do exactly this. Capture those modes, and you can rebuild the essential motion from a few coefficients instead of a full field, and even project how they will evolve. The modern surrogates go further. Neural operators don't just fit numbers. They learn the solution map of the underlying equations, taking inputs straight to full output fields. Train one on how a plasma responds, and it emulates the solver itself, orders of magnitude faster, while still returning a full field rather than a single number. That is the difference between predicting one summary quantity and predicting the whole picture at once. We keep the physics honest inside these models. Physics-informed neural networks fold the governing equations directly into the training as a penalty, so the surrogate is rewarded not only for matching data, but for obeying conservation laws. It learns physics, not just correlation, which is what lets it extrapolate sensibly instead of falling apart the moment it steps outside its training data. A prime target is turbulent transport, the churning at the plasma edge and core that sets how well heat is confined, and one of the most demanding things in all of fusion to compute from first principles. A fast transport surrogate lets the twin ask, "What happens if we nudge this?" and get an answer in time to actually use it. That single capability turns a class of overnight calculations into something a control loop can consult. Speed is only half the deal. The other half is knowing when to trust it. A Gaussian process surrogate returns not just a prediction, but an uncertainty band. Wider where it has seen little data, narrow where it has seen much. It tells you, plainly, when it is guessing. So there is always a dial between speed and accuracy. A leaner surrogate is faster but coarser. A richer one is slower but sharper. Choosing the right point on that dial for this decision at this moment is the engineering judgment that makes the whole system practical. A real-time controller and an overnight design study sit at opposite ends of that same dial. This is where surrogates earn their place. They are the fast inner engine of the digital twin and of every optimizer that searches for a better operating point. When a Bayesian optimizer proposes thousands of candidate settings, it is surrogates that let each one be evaluated in the time a real experiment would take to breathe. And we hold the line on honesty. A surrogate is an approximation, validated against the full physics it stands in for, and every one of its predictions carries an error bar. We publish the models and the validation openly, so anyone can check where the stand-in holds and where it does not. Fast is only useful when it is also trustworthy, and we insist on both.